In the previous episode, we learned how and why water moves underground, and we learned about the properties of rocks that control that. We even learned how it can impact your health if you have a septic and well water system on your property that are located just a little too close to each other, or if your water usage is a bit too high. Today we're going to explore what happens when water reaches the surface. How do springs work? And how does groundwater control every single landscape on Earth? I'm Craig the geologist. Come find out with me. Now let's talk about what happens when the water table intersects the ground surface. What happens when elevation drops below the level of the water table? All right, let's have a look at some land in profile. We're looking side on, and we've got a hill. We have a green hill that comes down like so. And the water table here tends to follow the land surface, but it doesn't drop at quite the same rate as the hill. Well, what happens right here is that the water table wants to continue out in the way it's been going, but it can't. Why? Because there's no ground. It can't be groundwater anymore. What happens there? Well, that is where it flows out of the ground. And that is where you have a spring. I'm at Iorgo Springs, a beautiful natural spot where the water is flowing right out of the ground. It's on the Asable River, not far from where I live. And the water flows right out of the dirt just above these weirs here, which, believe it or not, are completely natural. The beavers love to dam anything along the water's path, and they are really remarkable engineers. Iorgo Springs is a gorgeous little site located just a few miles outside of Oscoda, Michigan. Here, the springs flow right out of the hillside, form a very complicated network of braided channels flowing into the Asable River, where it's been dammed to form Cook Pond. The location is just a couple of miles outside of Oscoda, and it's free to visit. It's a beautiful spot, and I highly recommend it. Honestly, the sounds out here are as beautiful as the sights. And so, without any more voiceover or any background music, let's just listen to it. Well, now I'll bet a certain number of you are thinking, oh, this is gorgeous, I'm enjoying the view, but isn't this supposed to be educational? Where are those springs at? Well, let's take a look at how these springs come out of the ground and where, and learn a little something about them. So behind me here is one of the smaller streamlets that comes out of Iorgo Springs. Iorgo being a Native American word meaning many waters. I don't believe that's well documented, but that's the story that's been passed down. And you do have many waters here. These springs pop up all along this hillside. But right back here, at the base of this very tall hill, I'm pretty winded here, there is a layer of dense clay. Now, we associate clay with being wet, and so it might be surprising to you to find out that water hates clay. Water just can't move through it. That's why we associate clay with being wet, because the water that gets in there gets stuck in there and has a real hard time coming out. Water moves very easily through, gravel, through sand. But you reach clay, it becomes an impenetrable barrier. In fact, contamination ponds, landfills, any place where engineers don't want nasty groundwater seeping through, they line those things with clay. And so here we have that natural situation. Water filters down through the hillside, and gravity wants to take it down, but it hits that impenetrable clay layer at the base of this hill, and then it can't go down anymore. It's like laying a tarp down there. It can't go through it. So what it do? It goes horizontal, and it comes out right here. This little stream is perfect for us because I'm not going to get soaked. Let's go up the hillside a little bit and see if we can find the muddy spot where the water actually comes out. Well, here we go. Here's one of our springs. The water's coming out of the ground right in that spot over there. We come this way. We can see that the majority of this spring is just water bubbling up through the mud. If you're picturing something real beautiful with water fountaining out of the earth, sorry to disappoint you, but most springs start off as mud that gradually turns into a trickle, which turns into a little rivulet or streamlet or whatever you want to call it, and builds its way up into something a little bit bigger. Let's find the headwaters for this little stream. It's just mud, really. Water flowing right out of the earth. Nothing super dramatic. Just a spot where the earth sprang a leak. There are, of course, some places where the water issues forth a bit faster than others. And in those places, the water isn't seeping up through the mud so much as it's flowing more quickly from gravelly sand. And part of that is because the smaller mud particles have already been carried away by the water. And as the water makes its way downstream, it is remarkably clean because it just hasn't had much time to pick up biologic material that's going to dirty it. Here, the fast-moving water has done for you what the waves on the beaches tend to do, which is strip away all the fine-grained material and leave behind a lot of sand and glacial gravel. And that glacial gravel is the stuff we love to go rock hounding on. Now, is this a great place to go rock hounding? I wouldn't recommend it. I would prefer this place be left the way it is. I don't believe it's against the law. Is it unethical? We're in a gray area there. But this material here is going to be the same that you find on beaches all across the Great Lakes. It's stuff that was pushed down and left in glacial deposits during the last ice age. Now, generally speaking, an extreme case like I've drawn here is not a long-term situation. And why is that? Well, this is all saturated ground over here. And so you're going to have spring water leaking out all over the place here. And what's going to happen is that's going to lower your groundwater. That's going to lower your water table over time so that you end up with a situation that's a little bit more reasonable you're either going to fill up this space here with water, and this is your lake or ocean, or a river or stream, or the water is going to continuously drain away and your water table is going to be lowered to a point where it's only coming out right here. And now you just have a spring a little bit lower to the bottom of your valley or whatever. You're not going to have an entire saturated slope just leaking water for, 1,000 vertical feet. You'll just have a spring at the base of your mountain. Or you might have a spring at the top of your mountain, but that's forming a river and it's flowing away downstream. Now let's jump over to a very interestingly weird situation I found at Gratiot River County Park that almost perfectly illustrates the way these groundwater and spring systems work together. So, got a situation here that illustrates a man-made spring very well. So, here's a river, comes down here and exits out down that way. We have a perched pond here, higher than the stream down below. And someone has stepped into those rocks to create divots in there. It's now below the water table in the rocks there. And we have streams issuing forth the footprints. Perfect illustration of how ground level intersecting water table results in spring formation on a teeny tiny scale here. Let's talk for a moment about the three main situations you have where the water intersects the ground surface. If you've got a hill like this and a large depression with no drainage, you're going to end up with a lake. And the groundwater surface is going to be exactly at the elevation of the lake, at least within the first few couple of feet of ground. If you have a situation where instead of flowing into an area with no drainage, the groundwater is flowing into an area with great drainage, well, then that water is going to flow downstream. And you will have yourself a river channel. Where the water table on either side of the channel is exactly the same as the elevation of water inside your river channel. Finally, what happens when water flows out into an area that has almost no topography? Over here, the groundwater is just below the surface, but bam, it just intersects. And what do you get over here? Well, you get a wetland. You get a swamp. A swamp is just a place with generally very poor drainage, and I don't want to use that color, and just enough water to make everything wet and muddy, but not enough to create an actual lake. If you raise the elevation of the water table a couple of feet, you'll have a couple of feet of water in here, and your swamp might look more like a pond or a lake. But this is how swamps, wetlands of all kinds form. It's just the water table intersecting with the surface of the land, and there not being great drainage to drain it away like a river, and it's just not deep enough to be a lake. You got a swamp. You got mushy land. Now, There is an interesting feedback mechanism between lakes, rivers, swamps, and the groundwater slash water table. Now, we're going to ignore the case of swamps and lakes here because those are very stable long-term situations. They're not quite as dramatic as rivers, so we'll look at the river example. The same thing that happens in rivers can and does happen with lakes and wetlands, but we're just going to talk about the rivers here. So we have a river channel. We're going to look straight on at the river channel here. And we'll say the water is at this level. If this is a stable long-term situation and the water is almost always at this level, then the water table on either side is going to be the same as the river. Now, you can have two situations. One in which a river is flowing through the desert, as happens very often out in the desert southwest of America. You're talking your Utah, Colorado area. In almost all cases, the water table away from the river is actually going to be a lot lower. And so you will have the water table dropping away from the river as you go away from it, which means that the water, as it flows through, is going this way. Water wants to go downhill. And so the river is actually losing water the further it goes. And in fact, we see that at the Colorado River, after all the diversions and everything that's happened, the trickle of water that makes its way through California never actually makes it to Baja California. It doesn't even make it to the Mexican border anymore. It generally peters out. And it's not so much from evaporation, it's from the water leaving the channel through the ground and going into the groundwater. In most situations, especially in temperate areas, I live in Michigan, the water table will often be higher than the river. And so you'll end up with a situation more like this. And here, water is flowing through the ground and feeding the river through the channel. And the river gets larger the further you go, as opposed to shrinking. That's the more common situation, at least in places with healthy groundwater systems. Arid environments, which are unfortunately increasing, we'll see the opposite situation. Now, here's our stable situation. But what happens if there's a drought upstream and water is reduced? Let's say that there's no drought where we're at, but there's a drought upstream, or perhaps a dam has been constructed and it's been closed off and we've got reduced flow. Out in a lot of parts of the world, water gets diverted for farming. So perhaps it's a growing season and water is being diverted into canals and the water is exceptionally low. Well, the water is low in the channel, but the groundwater is still high. And so the groundwater level will start to drop near the river, but water will flow from the ground into the channel, kind of replenishing it. But the groundwater over time around it is going to gradually come down into something like this. Now, what happens if we have the opposite situation? There's a flood upstream. Happens all the time in India during monsoon season. Happens in California when there's snow melt on the Sierra Nevadas. This is actually a very common situation in downstream areas. Well, the water is in flood and it's significantly higher than the surrounding groundwater table. Well, what happens? Well, the water flows from the channel in there and gradually reduces as long as you don't have more tributaries coming in the same way that you get water flowing through an arid area. I had the opportunity to experience this a bit up close and personal just a few weeks ago when the Au Sable River decided to flood. I live on a floodplain. And you might be thinking to yourself, well, a geologist ought to know better than to live on a floodplain, especially one who back in 2010 helped his future wife evacuate through knee-deep waters during the Brisbane floods. It's an interesting life I've led, with many a misadventure, by the way. But aside from the fact that I purchased this place for family reasons, this area is actually one of the safer, maybe one of the safest floodplains there are. It's got a geologic reason for that. Not only are there 6 dams upstream that help regulate the flow of water and prevent flooding from happening during extreme rain events, but the geology of the area is sand. My hometown of Oscoda has dozens of miles of sandy beach that go in either direction, north and south, but they also extend inland. One thing a lot of folks don't realize is that for about 5 to 6 miles inland, the surface geology is all paleo beach. It is all ancient beaches that have since moved out further and further with the receding Lake Huron. This is a sand trail that extends out along those paleo beaches that I really enjoy running on. This is after a rainfall, but you can see it's just beach sand, but it's beach sand going miles inland away from the beaches. Now let's keep in mind a few things we've learned both in this episode and in the previous one on the subject. Sand, especially unconsolidated sand, beach sand, has a huge amount of porosity and amazing permeability. It can store a huge amount of water, and water can move through it very quickly. And so when you have a situation where the river rises, well, that sandy area can absorb a lot of that excess flow. Or conversely, where you have a situation where you have a lot of rainfall, there's not a dramatic amount of runoff into the river, because instead of all the water flowing over the land surface and reaching the river, it's absorbed by the ground and released more slowly into the river. And so the river tends not to rise very quickly. So isn't that fantastic that the floodplain where my house is built is flood-proof? But, oh wait, there's no such thing as flood-proof for any low-lying area, especially any floodplain. By definition, it's a place where there are floods. And so it's not flood-proof, it's just a bit more flood-resistant. So what happens when there is a 24-hour rain event that drops an unprecedented amount of water over the entire watershed? Well, the dams upstream have to release that flood water. And downstream, where all that water is going, the ground is already saturated from those 24 to 36 hours of non-stop torrential rain. And so you get flooding. Now, this was not a spectacular or particularly devastating flood event. There were no lives lost, and the property damage was in most cases pretty minimal. The river only rose about 8 feet above its normal level. But in an area where the river doesn't tend to rise at all, thanks to the geology of it, that's pretty significant because people build their houses right at that normal water level. My house was just fine. We remained about 6 feet above the highest level that the river reached. But there were a day or two where we were kind of biting our nails and wondering, how high is this water going to get? And also, could we stop getting subsequent rainfalls in the days after? Every time it rained, we were just like, no, we really don't need this. All of this to say that sandy geology does create a bit of a geological buffer against extreme flooding events, but it doesn't flood-proof any location. And with that, let's get right back to it. It's worth noting also that if you have a river that is significantly above the groundwater elevation, it's going to try to cut its way down to a more stable situation. So, for example, if using a red surface now, we're going to talk about the Colorado River here. If you've got a land surface here and you've got your river channel here, and water's flowing rapidly through it, but your water table is down here, what's going to happen is that over the next several million years, water is going to be being lost, of course, through here. But the channel is going to keep cutting its way down further and further, trying to reach the bottom of the water table, or the top of the water table, trying to reach a more stable situation. So over time, this will look more like this. The water flow hasn't increased, but is continuing to cut its way deeper. And give it a few more million years, and what you've got is a giant canyon if the rock unit is very strong, or a very deep valley if you've got softer units down there. So this would be like a straight on look at the Grand Canyon or at Black Canyon of the Gunnison. Whereas in softer sediments, like in my area in Michigan, especially in the Upper Peninsula, you do get occasionally very deep valleys where you're just driving along and there doesn't seem to be anything terribly interesting going on. And then all of a sudden, there's this incredibly deep valley and a stream that just seems too small to have made it down at the bottom. Well, what's happened is a very large amount of time and a very big difference between the groundwater elevation and the elevation of the water that was coming through in the first place. It cut its way down, and it cut its way down to a level where it could be stable with the water table. A lot of people think that canyons and valleys will cut their way down until they reach sea level or the level of the nearest lake. What they're really doing is they're cutting their way down to the nearest water level, but the water level that's really important to them is the groundwater level. It doesn't matter what the sea surface level is, what the nearest lake level is. The groundwater table, the water table is the important thing. And with that, I hope you'll join me for part 3 of this series, where we'll talk about more extreme cases of when water reaches the surface, particularly in terms of hot water systems, geysers, hot springs, fumaroles, and the minerals they bring to the surface with them. It's going to be real interesting. I hope you'll join me.